Random fields, spectrum recovering. Random field is just a linear combination of some basis function uk of x with random coefficient zk, xk. X is some, for example, special variable. If expectation of all of the coefficients is equal to 0 and they are independent from each other, then this value's expectation of ck squared is called the spectrum of the random field u in respect to the basis uk. Example: suppose that xi and eta are independent random variable with zero mean, and find the spectrum of the field u of x xi plus x eta. So we have only two basis functions, 1 and x, with and two random variables, xi and eta. And we need to recover the spectrum from the observations at 2 points, at 0 and at 1. This is simple exercise. Substituting here x equal to 0, we obtain that expectation of u of the observable u of 0 squared is exactly give us the first spectral component. Expectation of u of 1 squared at point x equal to 1, we just need to take squares and use the independence of random variable xi and eta, so the expectation of product xi and eta appearing, if we take the squares, disappear because expectation of xi and expectation of eta is equal to 0, 0 mean. So we have expectation of u of 1 squared is just a sum of two spectral components. Thus, the spectrum can be recovered from observables as expectation xi squared. The first component is just expectation of observable at point 0 squared, and second spectral component is the difference between squared observables at point 1 and at point 0. So this is simple example. Now the question to you. Can one recover the spectrum of the more complex random field xi1 plus x xi2 plus x squared xi3? So we have three basis functions, 1 x and x squared, 3 independent random coefficients with zero mean, and the question: how can we recover the spectral components, the expectation of xk squared, from two observables, u of 1 and u of 2? We should use the same scheme. We need to take the squares. But we have only two squares and we have three unknown parameters. So that's why you also need to use expectation of the product of the observables. If we have observable u of 1 and u of 2, of course, the product is also available to us. Try to solve this exercise. Central limit theorem. If xg are bounded identically distributed random variables with expectation mu and variance sigma, then the ensemble average of a large number of the components tends to the expectation, tends to the mu. And the second order term, if we take the difference mu minus the ensemble average minus mu, this is a small value. But if we multiply this small value by square root of n, this is already not small. And the distribution of this quantity is Gaussian when n tends to infinity. So this probability tends to this integral of Gauss kernel. The first example, one-dimensional random walk. We have many independent random variables which takes only two values, -1 and 1 with the same probability, 1 over 2. -1 corresponds to the step to the left side, and 1 corresponds to the step the right side. Starting from 0, the particle makes 10,000 steps. The question: what is the probability that the particle will be away from the starting point more than 50 and less than 100 steps? Solution. In this case, mu is equal to 0, because this is expectation, so -1 plus 1 divided by 2 is equal to 0. We already computed the expectation of such type symmetric random variables. And sigma is the expectation of xi squared, so -1 squared plus 1 squared divided by 2 is equal to 1. So we have two values, expectation and variance. Thus, by central limit theorem, we have this identity. But now, why we put here 0.5 and 1? 0.5, this is 50 steps, and 1, this is 100 steps. So we divided this by 100. That's why we put 0.5. And 100, this is 10 power 2 divided by 10 power 4. So we just put this factor here and here, divide by 100. And we did this because we need to apply the central limit theorem. And applying this central limit theorem, we approximate this probability with this Gaussian integral. The question why we put here the factor 2, because 50, the number of steps between 50 and 100 can be in the right side and on the left side. On the left side, this is particle, the position of particle between -100 steps and -50 steps. But because the Gaussian kernel is symmetric, it depends on x squared, these two probability from -100 to -50 and from 50 to 100 are the same. That's why we simply put here the factor 2, and we obtain this probability. Okay, now more examples on random walks. Again, Cg are independent identically distributed random variables that takes only two values, +1 and -1, with the same probability 1 over 2. From central limit theorem, we know that Sn, the sum of these random variables, grows as square root of n. This is visible from here because sum divided by n and multiplied by square root of n, this is the same like the sum xi1 plus xn divided by square root of n. So that's why the value, this sum divided by square root of n, is somehow bounded. So that's why this growth is of the order square root of n. We know that they grow as square root of n. This means that if we take power 2 of these two sides, then it grows like n square root of n power 2 is exactly n. And what is the constant c? And we can answer this question without applying central limit theorem. We just need to, we can simply use the independence and zero mean. So we have expectation of Sn squared, opening the brackets. We obtain sum of this expectation of their squares plus expectation of their products. But because they are independent, expectation of the product is the product of expectation. Each expectation of each of these random variable is equal to 0 because it takes ±1 with the probability 1 over 2. So that's why we obtain this simple identity. We already computed expectation of xi squared. 1 squared plus -1 squared divided by 2, this is equal to 1. So the constant here is simply c is equal to 1. Now the question to you, what happens if we take not square Sn squared, but we take modulus of Sn. Of course, if Sn squared is growing as c, as something like n, so this should be something like c multiplied by square root of n. What is c in this case? And surprise, c is not equal to 1. And to find this c, we need here to apply the central limit theorem. Try to solve this exercise. Next exercise is more complex. So these two exercises, last exercises, are very complex in some sense for the people who are not very familiar with the probability theory. Try to generalize this example to the case of 4 steps, not only left and right, but also up and down with the same probability 1 over 4. Try to find constant c in this case, expectation of modulus of Sn. Try to generalize the previous example to the case of 2D random walk, arbitrary angle, not only up, right, down, and left, but any direction. Try to find the constant c in this case. In these both examples, you need to apply central limit theorem. Try to solve this exercise, but this exercise is quite complex, so that's why I don't expect that many of you can solve this. But at the same time, this is very good exercises. If you can solve this, then you are in the advanced level in the probability theory. Thanks.